Imagine you're trying to solve a maze using a computer.
Every computer, even the most advanced supercomputer, solves the problem exactly the same way. It first explores one path in the maze, and if it hits a dead end, we need to double back all the way and restart by choosing a different path. This sequence is repeated until the solution, in this case, the exit, is found.
Time consuming, right? This is where quantum computing comes in. It's just an expression. It harnesses the weirdly wonderful phenomena of quantum mechanics to deliver a huge leap in computational speed, also allowing us to solve certain problems that supercomputers today cannot and probably never will. So, what are quantum computers?
On classical computers, information is stored using bits, where one bit can hold values 0 or 1. Quantum computers, on the other hand, use qubits, which are the quantum analogues of bits. A qubit is a two-level system existing as a linear combination of 0 and 1, meaning a qubit can harness properties of the quantum world to exist in a state of 0 and 1 simultaneously. Further, a system of 2 qubits would have 4 possible configurations, 3 would have 8, and so on. Extrapolating this, an n-qubit system has 2 power n possible configurations of bits, making the computational power much higher.
This allows for some very weird stuff to happen. Remember our maze?
Well, this is how a quantum computer would solve it, by harnessing the quantum property of superposition.
And that brings us to our next question. What in the world is superposition? In quantum mechanics, superposition means that a quantum state can exist in multiple states simultaneously. A famous thought experiment, Schrödinger's cat, explains this perfectly.
In this setup, a cat is locked up in a box with a tiny bit of radioactive substance and a mechanism attached to a hammer, under which is a flask of toxic gas. If the substance decays, the mechanism is triggered, smashing the flask and killing the cat. In the course of an hour, there should be an equal chance of the substance decaying or not, translating to a 50-50% chance that the cat is dead or alive when we open the box at the end of an hour.
Now, just before we open the box, it is theorized that the cat is both dead and alive at the same time, staying in that state of superposition until we conduct a measurement. This actually collapses the superposition, forcing the cat's state to be revealed: dead or alive, 0 or 1. Think of all the places where quantum computing would make breakthroughs like never seen before. Cybersecurity, artificial intelligence, financial modeling, computational chemistry, logistics optimization. The list just keeps growing. We may not be sure what the future has in store for us, but it's certain that small is the new big.